This video is about the greatest common divisor of two polynomials over a finite field. Our goals are to review the definition of the greatest common divisor of two polynomials over a field, and to work a few examples and concept checks, emphasizing finite fields. We will assume familiarity with the Euclidean algorithm for computing GCDs and for finding a linear combination of polynomials that equals the GCD. We will use the following definition. Let f be a field, and let f of x and g of x be polynomials with coefficients in f. The greatest common divisor of f of x and g of x over the field f is the unique non-zero monic polynomial d of x with coefficients in f, such that d of x is a common divisor of f of x and g of x, and if c of x is any common divisor of f of x and g of x, then c of x divides d of x. This is a standard definition for the GCD of two polynomials, and we include the requirement that the GCD be monic, i.e. the leading coefficient is 1, in order to ensure uniqueness. We will be working primarily in this video with the field ZP, where P is prime. Recall the following facts. The GCD of two polynomials is always the monic polynomial of greatest degree that divides both polynomials. Note also that the GCD depends on the field from which the coefficients are considered. For example, given f of x equals x cubed minus 8 and g of x equals 3x squared minus 6x, considered as polynomials with rational coefficients, the GCD of f of x and g of x over q is x minus 2. Whereas, if we consider f of x to be x cubed minus 8 and g of x to be 3x squared minus 6x, but where the coefficients come from z2, then f of x is actually equal to x cubed over this field, and g of x is equal to x squared. So the GCD will be x squared over this field. Recall that the Euclidean algorithm can be used to find the GCD of two polynomials over a field. Given f of x and g of x, polynomials with coefficients in a field f, we can use the division theorem to divide f of x by g of x to get a unique quotient polynomial q of x and a unique remainder polynomial r of x. In that case, you can show that the GCD of f of x and g of x equals the GCD of g of x and r of x, which enables the Euclidean algorithm to give us the GCD. As a quick example, consider f of x equals x to the fourth plus 2x cubed plus 2x plus 1, and g of x equals x cubed plus 2x squared plus 1, considered as polynomials with coefficients in z3. We will go through examples in more detail later. You should feel free to pause the video and work through the details of this one yourself before going on. But notice that on the first line, we have divided f of x by g of x and gotten a quotient and a remainder. And sure enough, the remainder is of degree 1 and g of x is of degree 3. So by our result, the GCD of f of x and g of x equals the GCD of g of x and r of x, x plus 1. Then we can make g of x into our new dividend and x plus 1 into our new divisor to get quotient remainder again, so that the GCD of g of x and x plus 1 is equal to the GCD of x plus 1 and 2. On the next line, the GCD of x plus 1 and 2 equals the GCD of 2 and 0. So our last non-zero remainder is 2. But be careful, the GCD must be monic. So we will take the monic multiple of the last non-zero remainder, which is 1. Our conclusion is that the GCD of f of x and g of x is equal to 1. For our next example, let f of x equal 3x to the 4th plus 6x cubed plus 3x squared plus 2x plus 3, and let g of x be equal to 2x cubed plus 5x plus 1, considered as polynomials with coefficients in Z7. First, we will divide f of x by g of x to get quotient and remainder as in the Euclidean algorithm. As a quick review of polynomial division, we can fill in our coefficients here. This is f of x, 3x to the 4th plus 6x cubed plus 3x squared plus 2x plus 3. And we're dividing by g of x equals 2x cubed plus 0x squared plus 5x plus 1. First, we need to figure out what can we multiply by 2x cubed to get 3x to the 4th. Now remember, we are working over Z7, not over Q. So there are no fractions. We should not put 2/3 here, because that's not an element of Z7. Instead, we need to ask, what element of Z7 do we need to multiply 2 by in order to get something that is congruent to 3 mod 7? And you can check that if you multiply 2 by 5, you will get 10, which is congruent to 3 in Z7. So here we're going to write 5x. Then multiplying this through, 5 times 2 is 10, which is 3 in Z7. So that's 3x to the 4 plus 0x cubed plus 5 times 5 is 25, which is 4 in Z7, and plus 5x. Now we subtract. 2 minus 5 is negative 3, which is 4 in Z7. 3 minus 4 is negative 1, which is 6 in Z7. 6 minus 0 is 6. So after subtraction, we have 6x cubed plus 6x squared plus 4x, and then we bring down the plus 3. Then we repeat the process. We need to put 3 here, so that 3 times 2 is equal to 6. And then we multiply by x cubed plus 0x squared plus 15x, which is the same thing as 1x in Z7, plus 3 times 1 is 3. Then we subtract. And so we have our quotient, 5x plus 3, that's our q of x. And we have our remainder, which is r of x. Performing polynomial division involves a fair amount of writing with all of the powers of x and placeholders, but all we really need is the coefficients. So from now on, all of the polynomial divisions that I will demonstrate, I will simply use the coefficients. You're welcome to do the computations on your own with the powers of x in there if you prefer. Okay, for the next part of our example, we're going to compute the GCD of f of x and g of x. We learned in part 1 that f of x is equal to 5x plus 3 times g of x plus 6x squared plus 3x. So now we get to divide g of x by 6x squared plus 3x to get quotient and remainder for our second step. So our coefficients look like 6, 3, 0. and g of x is 2x cubed plus 0x squared plus 5x plus 1, what times 6 is equal to 2? Well, 30 is congruent to 2 mod 7, and 30 is 6 times 5. So 5 times 6 is 30, which is 2. 5 times 3 is 15, which is 1. 5 times 0 is 0. Subtracting, 5 minus 0 is 5. 0 minus 1 is negative 1, which is 6 mod 7. And then we bring down the 1. 1 times 6 is 6, multiplying through by 1. And then subtracting. Here we have the equivalent of 2x plus 1 as our remainder, and the degree is 1, and which is less than the degree 2 divisor, so that's our remainder, 2x plus 1. And our quotient is 5x plus 1. So now we keep going. You'll notice that I've underlined the important parts of each equation. That helps distinguish the f and the g and the r from the quotient, which is not as important. So now we divide 6x squared plus 3x by 2x plus 1. To get quotient and remainder. And I'll just go through that quickly, but you're welcome to pause the video and work it out for yourself more slowly if you need to. So 630 divided by 2, 1. 3 times 2 is 6. 3 times 1 is 3. And now we have our 0 remainder. But this is actually 3x because there's another 0 here. This is 0x plus 0. And so our quotient is 3x and our remainder is 0. So here is our last non-zero remainder, 2x plus 1. But that's not the GCD because 2x plus 1 is not monic. In order to get the GCD, we need to factor out the 2 to find out what multiple of 2x plus 1 over Z7 is monic. Well, observe that 2x plus 1 is equal to 2 times x plus 4. If you multiply it out, you can see that that's what we get. 2 times x is 2x, 2 times 4 is 8, which is 1 in Z7. So the GCD of f of x and g of x is x plus 4 over Z7. For the last part of this example, we want to find polynomials m of x and n of x with coefficients in Z7 such that the GCD of f of x and g of x is equal to this linear combination of f of x and g of x, m of x times f of x plus n of x times g of x. One convenient plan is to reverse the steps of the Euclidean algorithm to write 2x plus 1 as a linear combination of f of x and g of x, and then factor out a 2 from both sides, which will leave us with the actual GCD as a linear combination of f of x and g of x. Okay, so here are the steps that we took in the previous part, and we will use these to calculate our linear combination. So first, using this equation, I'll call this equation A. So using equation A, we can see that 2x plus 1 is equal to g of x minus the quantity 5x plus 1 times 6x squared plus 3x. Then, using the other equation, equation B, we can replace 6x squared plus 3x with f of x minus 5x plus 3 times g of x. Now everything on the right-hand side of this equation is a linear combination of f of x and g of x. So now we just have to combine the like terms. We get minus the quantity 5x plus 1 times f of x plus 1 plus 5x plus 1 times 5x plus 3 times g of x. Further simplification gives us this. Negative 5x is the same as 2x in Z7. Negative 1 is 6. Then multiplying out this factor and combining the like terms and taking everything mod 7 gives us 4x squared plus 6x plus 4. Now we're not quite done with our task because the task is to express the GCD of f of x and g of x as a linear combination of f of x and g of x. So our final step is to factor out a 2. We've already seen that 2x plus 1 is equal to 2 times x plus 4. 2x plus 6 is equal to 2 times the quantity x plus 3. And 4x squared plus 6x plus 4 is equal to 2 times the quantity 2x squared plus 3x plus 2. Therefore, x plus 4 is equal to x plus 3 times f of x plus the quantity 2x squared plus 3x plus 2 times g of x. So we may use m of x equals x plus 3 and n of x equals 2x squared plus 3x plus 2. Here we come to a concept check. Pause and explore. I urge you to pause the video and work out the answer for yourself before continuing. Let f of x be equal to 2x to the fourth plus 3x cubed plus 3x plus 3, and g of x equal x cubed plus 4x plus 1, considered as polynomials with coefficients in Z5. In the first part, find the GCD of f of x and g of x. And second part, find a linear combination of f of x and g of x that equals this GCD. Pause the video and work out the answer to at least the first part before continuing. Okay, so for part 1, we are looking for the GCD of f of x and g of x. So let's use the Euclidean algorithm and divide f of x by g of x and get quotient and remainder. 2 times 1 is 2. 2 times 0 is 0. 2 times 4 is 8, which is 3 in Z5. So maybe we'll note here that we're working over Z5. 2 times 1 is 2. 3 minus 2 is 1. 0 minus 3 is negative 3, which is 2 in Z5. 3 minus 0 is 3. Bringing down the 3. We need 3 here. 3 times 1 is 3. 3 times 0 is 0. 3 times 4 is 12, which is 2 mod 5. 3 times 1 is 3. 1 minus 2 is negative 1, which is 4. 2 minus 0 is 2. So our quotient is 2x plus 3, and our remainder is 2x squared plus 4x. So now we need to divide g of x by 2x squared plus 4x. What times 2 gives us 1 in Z5? We can use 3. 3 times 2 is 6, which is 1 mod 5. 3 times 4 is 12, which is 2 mod 5. And 3 times 0 is 0. Subtracting. 4 minus 0 is 4. 0 minus 2 is negative 2, which is 3. Bring down the 1. In order to get something that is congruent to 3 mod 5, we can multiply 2 by 4. 4 times 2 is 8, which is 3 mod 5. 4 times 4 is 16, which is 1 mod 5. And 4 times 0 is 0. Subtracting, we get a remainder of 3x plus 1 and a quotient of 3x plus 4. Finally, we divide 2x squared plus 4x by 3x plus 1, and we get 4x plus 0 with a remainder of 0. Therefore, 3x plus 1 is our last non-zero remainder. So in order to get the GCD, we simply have to factor out our leading coefficient of 3 to get the monic greatest common divisor. When we factor out a 3, we get x plus whatever we have to multiply 3 by to get 1, which is 2. So the GCD of f of x and g of x is x plus 2. If you haven't yet worked out the second part for yourself, pause the video now and work out a linear combination of f of x and g of x that equals the GCD. So again, using our previously obtained equations, I'll call this equation A and this equation B. We have 3x plus 1 equals g of x minus 3x plus 4 times 2x squared plus 4x. Then we can substitute to get g of x minus 3x plus 4 times the quantity f of x minus 2x plus 3 times g of x. Combining like terms and simplifying, we get 2x plus 1 times f of x plus x squared plus 2x plus 3 times g of x. The actual GCD of f of x and g of x is x plus 2, as we've worked out, so we need to factor out a 3 on both sides of the equation. Factoring out 3 from 3x plus 1 gives us 3 times x plus 2, as we saw before. Factoring out 3 from 2x plus 1, we must figure out what we have to multiply 3 by to get 2 mod 5. Well, if we multiply 3 by 4, we will get 12, which is congruent to 2 mod 5. And then 3 times 2 is 6, which is 1 mod 5. Over here, 3 times 2 gives us 1 mod 5. 3 times 4, as we saw before, gives us 2 mod 5. And 3 times 1 gives us 3. Therefore, x plus 2 is equal to 4x plus 2 times f of x plus 2x squared plus 4x plus 1 times g of x. And therefore, we may use m of x equals 4x plus 2 and n of x equals 2x squared plus 4x plus 1. The polynomials m of x and n of x are not unique, but the Euclidean algorithm gives us a way to obtain polynomials that do work. So to summarize, the GCD of two polynomials over a field f is the unique monic polynomial with coefficients in f of greatest degree that divides both polynomials. Given polynomials f of x and g of x with coefficients in a field f, we can use the Euclidean algorithm to find the GCD of f of x and g of x over f, and to find a linear combination of f of x and g of x that equals this GCD. And as we have seen, computations, such as polynomial division, are performed using operations from the given field. In particular, when the field is ZP, there are no fractions. I hope you found this video helpful.